Hello and welcome to our webinar on plastic composition and restricted materials. I'm Bruce Calder. I'm VP of Consulting Services and Operations at Claigan. So I'm going to talk about a lot of things. It says Reach SBHC database at the top. We're talking about plastics mostly. We will talk a little bit about the SCIP database, Reach SBHC database. It's a good reminder off the bat of the January 5th, 2021 deadline to register products with any component with an SVHC above 0.1% by weight in Europe. And it kind of feeds into the second section. We're mostly talking around plastics, and we're going to be very specific. We're technical to a point. We will talk some little bit of depth around flame retardants, but we're going to talk about what's in plastics. And then we're going to focus very heavily on an example one. We want this to be tangible. So we're going heavily after what's in or potentially in a PVC jacket for a USB cable. It's a pretty good example of pretty well everything you could possibly find in there. And the reason we're not doing this is we get non-compliances for RoHS or Reach SBHC or Prop 5 on a regular basis for plastics, and want to explain where the non-compliances are coming from, but really why they're there. So it makes sense that going through step by step all the things that are in plastic. And we're going to use a very specific example. It's a lot more tangible. We talk about something that you can recognize and touch and have a better understanding of. So it should be about 50 minutes. It was 50 minutes this morning. There are lots of great questions. We'll have Q&A at the end. If you have any questions during, feel free to submit it in the control panel, and I'll try to get to as many as possible. It's going to be technical. Afterwards, probably by tomorrow, maybe a day later, we should have a recording of this available online. We should also have a YouTube version. The huge advantage of the YouTube version, so I'm told, is you can scroll back the speed to 70%, and I might actually make some sense. Definitely, we have some people here that have mentioned now they can scroll back to 70%, they can understand me. But I don't want you sitting here and as I pedantically go through things, I'm going to move with some speed. Of course, if you have questions, feel free to submit. So first off, the SCIP database, the Substance of Concern in Products, a very interesting acronym from the EU, formerly related to the Waste Framework Directive or the REACH SVHC component of the REACH regulation. It's kind of changed names, the Waste Framework Directive database and REACH SVHC database. The Substance of Concern database is now the Substance of Concern in Products database, the SCIP database. Database should open around January next year. It's probably be a tiny bit late, but probably not as much as people think. The fellows writing this, the people's writing this, have been writing in EU Euclid, their software, for over a decade doing chemical registration, and are actually pretty good at this sort of thing. And the deadline, unless some unforeseen delay, is companies have to register their products in the database by January 5th, 2021, if any component in their product has an SBHC, a substance of very high concern, above 0.1% in any of the components. When you see something like electronics, almost all electronics have one. They'll have a brass standoff. You take a very common plug-in consumer product, one of the pins in the power cord itself, you plug into the wall, will have leaded brass. Anything with a button cell battery will have it. Silicone often has D6 cyclosiloxane. It's very, very, very common. All products are in scope. There is a military national defense products can choose to be out of scope, but basically everything's in scope of this. So electronics, non-electronics, consumer, professional, everything has to go in here if any component is an SVHC over 0.1% by weight. Key deadline, of course, January 5th, 2021. However, most of the work will have to happen next year. You need to basically create the REACH SVHC declaration, which by law you're already supposed to have on hand. Then you want to create the SCIP declarations. We usually have this interim step where we prefer a Google Sheets version. It allows multiple stakeholders to look at the data in common. And there will be multiple stakeholders for both data and review. There's technical information like materials and SVHC, but there's sales information like part numbers and such. And then there's also trade compliance stuff like customs codes and stuff like that. We find it very helpful to use Google Sheets. Send it on an Excel sheet with vision control is messy. We prefer a central place to work in, especially multi-stakeholders. And then once you create that in the fields, the mandatory and the optional, submitting it to the database will be relatively straightforward. Just a matter of doing the fields properly. The main work is creating the declaration itself and then getting into an agreed upon data set, which we do in Google Sheets, and then submitting it. But a lot of the work, of course, since it's January 5th, 2021, happens next year. And one of the fundamental rules about restricted materials compliance is restricted materials prime can do anything they want as long as it's free. And this kind of effort isn't. So companies often have to plan ahead and make sure you have the resources to make sure this occurs. Refrigerator revisited. So we've talked about this in previous webinars. We're going to move beyond skip in a moment onto plastics. But again, you take a refrigerator that has a copper component with leaded brass in it. You have to identify the component, the fact that it's lead in, about 0.1% by weight. It has a silicone washer or seal with siloxane, D6-cyclosiloxane above 0.1. You have to identify each component that has an SBHC above 0.1% by weight. If a component does not have an SBHC above 0.1% by weight, you don't have to identify. But the main product has to be identified in each component or component type that has it. And then you have to move from that representational one to this is what we often look like in Google Sheets. We create the main complex article version, which will link to a smaller version you do for the standoff and a smaller version you do for the washer. We prefer doing this, of course, in Google Sheets because you can put all your products next to each other. You can copy data across. Multiple stakeholders can fill in their sections together, and then it's relatively straightforward to put into the database itself. So why this is really relevant, of course, is we're talking about a lot of substances of concern and restricted materials, and that comes back to plastics and what's actually in plastics. So good question for everybody. What's really in plastic? Hey, that's just PVC. It's maybe 50% polyvinyl chloride. It's 50% other stuff. And why do we find restricted materials often in plastics? We test all the time. We're a very high volume lab in this space. We test plastics all the time. We get non-compliances very regularly in plastic, whether for RoHS or REACH SBHC or persistent organic pollutant or other regulations, Prop 65. There's a reason they're there. So for representational purposes, we've picked an imaginary, these are just stock photos, orange USB cable. And we're going to talk about the outer PVC jacket of the cable. It's very tangible. It's a very common type item. It'll hopefully help us explain what's really in here. So PVC. PVC has a lot of stuff in it. PVC is polyvinyl chloride. Of the PVC cable jacket, only half of it is really PVC resin. The other half is other stuff. The next one is a plasticizer. So you take PVC. PVC's natural state is rigid, it's like your water piping. To make it bend, you have to add a plasticizer. And the way they work is they basically work like a fluid. They get between the vinyl chloride strands, PVC's polyvinyl chloride, get between the strands, push them farther apart, action called swelling, like you do in a sponge, you make it swell. They push the strands farther apart and reduce their bonds of attraction. So you take two magnets, put them right together, they're pretty hard to move. You put a magnet in each hand and put them an arm's length apart, they're really easy to move. They have very weak bonds of attraction. And that's what it's basically doing here. The plasticizer, which is basically a fluid, is getting between the polymer strands, pushing them farther apart, which creates more fluidity, which is the flexibility. And that's the difference between a power cord, flexible, and a water pipe, PVC pipe, rigid. It's the plasticizer. It's basically a fluid. It's not a permanent part of the polymer. It just gets between the vinyl chloride strands and pushes them farther apart. PVC can burn. When it does burn, it creates often hydrochloric acid. It'll create hydrogen radicals, we'll talk about later, which is a lot of the heat and color you see. And the basic goes into runaway and burns. So in electronics in particular, PVC you don't want to burn, so flame retardants are added. These are things to stop the runaway process, flame and damp it down so it doesn't have the energy created to create the runaway burn. And we'll talk a lot more about flame retardants in detail. Then there's a filler. For a variety of reasons, there's filler in here. It's often because it's cheaper or to achieve some physical property. And in certain cases, they have some flame retardancy effects of their own. But it's actually a filler, like calcium carbonate. Next one's pigments. So it's not color or dye, it's pigments. We'll talk a lot about pigments. Pigments is a separate plastic, which is colorized, that's added to the PVC to create the color you see. So we're going to talk more about pigments or the coloring. Stabilizers. PVC is not naturally thermally stable. At different temperatures, the durometer, i.e. softness or flexibility, will change. It'll also potentially degrade with different temperatures. So it has stabilizers in it to prevent a significant change physical properties with temperature. Also, if the cable has to go outside and it's exposed to UV light, it often needs UV stabilizers to stop sun fade or degradation in the sun. So PVC normally stabilizers, at a minimum thermal stabilizers. They'll often have a very small concentration of antioxidants. So when the PVC is extruded into the cable form, it doesn't react with the oxygen and create a burnt effect. The burnt effect not only changes color, but it changes the physical properties. As it oxidizes or physically has a burnt effect with the atmosphere, with the oxygen in the atmosphere, it will change the color, degrade the plastic. And so often it needs an antioxidant to prevent that from occurring. And then most cables have a lubricant, and the lubricant is not really part of the PVC, it's basically separate. But it'll usually have a silicone oil, or in bigger cables, talc powder, to create lubrication inside the cable, where the inner wires want to slide independently of the outer wires, or you have to slide one inside the other, and it creates lubrication or reduces friction between the inner wires and the outer jacket. So it allows them to slide as it bends. There's often a lubricant, which could be silicone oil, could be bigger cables, could be talc. So that's awesome. That's a starting point. So the starting point to understand is PVC jacket is usually maybe 50% polyvinyl chloride. There are other things in it. So I'm going to go over each one. So polyvinyl chloride is polymerized vinyl chloride. And that part of it will be primarily 99.9% plus percent PVC. It will have a token amount of unreacted residual monomer, typically around 10 ppm. So if you get a safety data sheet for PVC, you'll often see in section 15 for Prop 65, a Prop 65 warning for vinyl chloride, which is a residual monomer. It's typical, not fully polymerized PVC, but very, very low concentrations. Now, the plastic supplier provides a warning because they provide usually pellets or flakes, and they can be inhaled, and the worker could be inhaling them as a dust, and the plastics provider doesn't know what ventilation they have, and so they provide a warning for the vinyl chloride. But this is really for airborne. The vinyl chloride warning, the safety data sheet, is not for your cable, it's for the bag of pellets or flakes they provide, which can be inhaled. The vinyl chloride itself is not an exposure risk when it's in the final cable form. So this is one of the things where you're going to see differences or discrepancies between what a supplier potentially reports for Prop 65, like vinyl chloride, and what really applies to your product. Because the safety data sheet, where most people get the data, is for the bag of pellets or flakes. It's not for the final product. It doesn't have a safety data sheet. So you'll see this disconnect commonly. Then the plastic will have a plasticizer, and usually more than one. So it'll have a primary plasticizer and often a secondary plasticizer. Now, the primary plasticizer historically are orthophthalates. It's been changed a lot of products recently. PVC use different plasticizers, usually of similar families, usually terephthalates. So what makes orthophthalates or DHP dangerous is DHP is not in of itself dangerous, but once you metabolize, your liver metabolizes it, you end up with a metabolite which is similar enough to estrogen to create an estrogenic or female body response. And that's the reproductive toxicity. The replacements are structurally very similar, like the terephthalates, however, they do not metabolize in the same dangerous form. So you have a plasticizer like DHP, and then you can have a secondary plasticizer like short-chain chlorinated paraffins or medium-chain chlorinated paraffins. And what secondary plasticizers do is they don't make the plastic more flexible. They enable the primary plasticizer to do its job better. So one of the challenges with DHP, it's fundamentally a fluid, and it wants to leave or migrate. You put two flexible PVCs next to each other, or even a flexible and a rigid, the phthalate from one will migrate in the other. It's fundamentally liquid. The secondary plasticizers make the primary, so SCPs make orthophthalates more compatible with the PVC. So less likely to migrate out, and you don't need as much of it. So short-chain chlorinated paraffins are called secondary plasticizers, but they aren't actually plasticizers. They enable orthophthalates to be more compatible with PVC. There's a number of advantages in that. One, they don't migrate as much out of it. But one of the other big advantages is it's cheaper. So DHP, or most orthophthalates, are about $1,300 per ton. The replacements, terephthalates like DOTP, are very similar in price. One of the reasons why terephthalates are a common replacement for orthophthalates. However, the orthophthalate chlorinated paraffin 52 blend. Chlorinated paraffin 52 blend is chlorinated paraffins controlled to 52% chlorine. In theory, on average, they're medium chain chlorinated paraffins, which aren't regulated yet. However, it's on average. They only control the chlorinated paraffins by chlorine content. So about 20% of MCCPs, medium chain chlorinated paraffins, are actually short chain, which are banned in Europe and Canada. So because of this, the CP52, or the short chain chlorinated paraffin, and DHP blend ends up being about $600 and some a ton, which is about half the price of DHP alone. So for cheaper plastics, we will very commonly see SCCPs because they're part of the chlorinated paraffin 52 that's been added to DHP, and it's a cheaper effective plasticizer where the cheap SCCPs enable the DHP to better be integrated with the plastic. So when we see SCCP failures, it's always in combination with orthophthalates. They enable orthophthalates. They don't exist normally in PVC without orthophthalates. They are not a plasticizer in of themselves. They enable the orthophthalate to be more compatible with the PVC. And there's usually a bit of antioxidant, which is commonly bisphenol A. So bisphenol A is a very common antioxidant for orthophthalates. So the plasticizer itself will have an antioxidant, and that antioxidant will be in higher concentrations than the antioxidant for the PVC itself. It'll be up to 2% of the plasticizer, maybe a little bit less, maybe about 1% or less. However, in the final product, you'll end up with a couple thousand ppm of BPA. So when we see a BPA non-compliance over 1,000 ppm PVC, it's normally coming in through the plasticizer, not through the PVC itself. It's coming in as an antioxidant. It's only normally very effective with the orthophthalates like DHP, but we commonly see the BPA as the antioxidant with orthophthalates. There are other antioxidants that are being further regulated. TMPPs, one of the most recent ones, is another phenol. It's operationally very similar to BPA. They have similar structures. It has something to do with the phenol group and why they're such good antioxidants, which the antioxidants' job is to prevent the chemical from oxidizing or getting burnt by the oxygen in the air, by reacting or oxidizing or rusting in the air, which would create a color change and potentially a materials change. So when we get a BPA failure in PVC, it's normally coming through the plasticizer, which uses an antioxidant to when the material is extruded or otherwise used, the plasticizer doesn't get oxidized. Next one's a flame retardant. Now, normally in a flame retardant, we see two groupings. We see a flame retardant, often a halogenated one like bromine or chlorine, and then a synergist. So if you take heat shrink, polyolefins, very thin plastics have a hard time meeting ULV 0. They have trouble passing the candle test. Thin plastics have a lot of trouble passing the candle test. So they either need a lot of flame retardant, but if you put too much flame retardant in, you get to the point where the plastic is no longer a plastic anymore. And that doesn't work out too well. So most halogenated flame retardants use a synergist, which the most common one is diantimony trioxide or antimony trioxide. And it works in common with a halogen flame retardant to ensure that less halogenated flame retardant is required. So if you're using a synergist, you don't need nearly as much brominated flame retardant. And we see this with Deca BD, which is the only RoHS polybrominated diphenyl ether we ever really see. It's always in present with antimony trioxide. With it present, you don't need nearly as much bromine, flame retardant. And the bromine and halogenated flame retardants are very important types of flame retardants. They're all chemical gas phase. What they do is the fire is occurring on PVC, one, hydrochloric acid is produced, but hydrogen radicals and OH radicals are created. So if you take salt, sodium chloride, and you put it in water and you get sodium ion, Na+, and a chlorine ion, Cl-. Everybody's used to ions. And what those are is they're the individual elements, in their case, that have gotten or lost an electron and now have a positive or a negative charge. A radical is the same sort of thing, except for it hasn't exchanged electrons. It is extremely unstable. It's not a positive or a negative. It actually hasn't exchanged electrons at all. And these are often in plasma. It's the color you see from flame or fire. It's often the inside the H radicals. It's the burning spectral but a lot of them are H radicals in there. And so H plus is an acid, and OH minus is a base. H radical is even more reactive. So as an acid can react with things, H radicals are even more reactive. They're very high energy. What happens in this is that through a fairly straightforward reaction, the halogen, bromine or chlorine, collides with the hydrogen radical and then cause the hydrogen to react with another substance and reduce in energy. And then the chlorine becomes a chlorine radical, the bromine becomes a bromine radical. And the chlorine and bromine are much bigger molecules than hydrogen, and they are less energetic or unstable, and they slow down the reaction. The synergist in antimony trioxide, antimony or antimony, does the same thing. It can also join into the equation and further damp down the production of hydrogen radicals. And so basically damps down the exothermic or energetic effect. So if you have antimony with the bromine or chlorinated flame retardant, you need a lot less of it, because in combination, they do a much better job of damping down the hydrogen radicals, the overexcited hydrogen particles, and stop the runaway fire we can have with PVC. So most flame retardants, especially the halogenated ones, normally end up, so it could be dechlorine plus, it could be DecaBD, normally end up with the antimony trioxide synergist. They enable less flame retardant to be used to create the same flame retardancy. So when you look at a flame retardant, you almost always have flame retardant and a synergist, especially in the halogenated ones. Now, one of the things we're going to take a little bit of a chemistry digression. I might have mentioned earlier I might do some chemistry, and the last part, of course, on radicals. Maybe I should have had pictures. That probably would have helped or not mattered. So because the Swedish flame retardant tax, people have a lot of questions about what's an additive flame retardant and a reactive flame retardant. So I want to explain that because it also affects what can be tested for. So a reactive flame retardant is a flame retardant that reacts and becomes part of the polymer. It's no longer a separate chemical, it's bonded in. So tetrabromobisphenol A is a very common flame retardant in FR4, which is basically polycarbonate. So the tetrabromobisphenol A actually merges and becomes part of the polycarbonate polymer. So if you look in the bottom right, it's all merged together. Polycarbonate is really a repeating chain of bisphenol A and phosgene. Bisphenol A is the one, sort of the two benzene rings there, and it attaches to a phosgene, which is kind of a little triangle. It's got a double bond O sticking up. It's kind of like your Klingon spaceship there. And polycarbonate is just BPA, phosgene, BPA, phosgene. Well, tetrabromobisphenol A is very similar. It's basically bisphenol A with bromines attached to 2 points. And so it merges right in. It jumps right in where you'd have a bisphenol A. It just has some bromines there and provides ready halogen or bromine to damp down the fire reaction. But it's reacted directly in. It's married to the molecule. It's not just dating, it's married. It's bonded in there. If it ever left, it would take something with it. Now, basically, if you pulled the tetrabromobisphenol A out, it's likely to pull a phosgene or phenol with it. So the separation there, now they're married, is much more serious than it would be if they were just dating. So reactive ones are ones that are reacted directly into the polymer, now part of the polymer. And if we tried to test for it, we wouldn't get tetrabromobisphenol A. Sure, we can measure bromine because of its elemental presence, but because the tetrabromobisphenol A is merged with the polycarbonate, unless we rip the polycarbonate apart, we won't see the tetrabromobisphenol A because it's fully reacted, now one with the polymer. The additive ones are different. They don't chemically bond to the polymer. They're just dating. They might touch a little bit. They might get close. But if one leaves, he's not taking anything with it. So the DecaBDE in polyethylene, so polyethylene or polyolefin heat shrink, often uses DecaBDE. DecaBDE is not part of the polymer. It's just an additive. So one of the reasons why we test polyolefin for Deca, we can test it directly because it's not permanently bonded to the polyethylene. It's just dating or touching. It can swipe left and move on from there, and no harm, no foul. As opposed to reactive ones, if you try to get the tetrabromobisphenol A out, they're fully married. It's going to rip stuff out. Somebody's going to get the phosgene. So basically, the tetrabromobisphenol A will say, hey, look, I'm taking the phosgene with me. You can keep the phenol. It's going to be pulled apart, and there's going to be a custody battle if you try to get the tetrabromobisphenol A out of there. In this one, the Deca is not that attached. It's kind of touching. They're dating, but you can swipe left and move on. Put it in perspective. So that's the big difference. And from a testing point of view, the additive ones we can test for directly because they're still themselves. The reactive ones are now part of the polymer, and they're no longer, without tearing the polymer to shreds, a separate chemical. So it's one of the big differences. And one of the reasons why additive flame retardants are usually more regulated is because they're more free to move and react and cause harm. They get out in the environment. Well, the reacted ones, like tetrabromo bisphenol A in FR4, aren't going anywhere. They're embedded in the polymer. There's a lot of conversation right now of adding potentially tetrabromo bisphenol A to RoHS. It won't make any difference because once it's used in FR4, it's fully reacted in. If you test for it, you won't find it, or at least just residual concentrations. So it wouldn't make any difference. They add it, even though it's in the FR4 board, it's not there anymore. It's not like DECA, which isn't permanently attached, or the phthalates. So we mentioned earlier, the phthalates, again, are between the vinyl chloride strands. They don't become part of the polymer. They get in between the vinyl chloride strands, and they are not attached either, which is why you can test for them. It's also why they migrate out. They're not permanently part of the polymer. So the next one's filler, which is pretty boring. It's like fills up extra space, either because of cost or physical properties. Now, calcium carbonate, which is one of the most common fillers, and we see a lot of calcium in a PVC, that's calcium carbonate. It also can add some physical properties and has some level of flame retardancy on its own. It doesn't really burn. Calcium carbonate doesn't burn very well. And there's often filler. And big power cables usually have more filler than little USB cables. But there's often filler. Filler is also, calcium carbonate is usually much cheaper than any of these other specialized plastics. Then there's pigments, which is probably the most misunderstood chemical group in PVC. So people are often, I guess, biased on what pigments or colorants are in plastics because of tie-dye shirts, where growing up, you take a tie-dye shirt, you have a liquid dye, you dip part of the shirt into the dye in different colors, it's a liquid, and that's what you're used to. It's very different in plastics. A pigment in plastic is a separate plastic. It has a carrier. So the pigment's not a liquid, it's usually a powder. The powder is usually just very small pellets, very small controlled pellets, which will disperse in the PVC when they're added to add color. But it has its own carrier resin. The pigment for PVC is another PVC. It needs the carrier. So it has PVC of its own. Then it'll have the colorant, which creates the color, and it's often a metal complex because the metals often create the color. It'll have a colorant, which could be azo dyes. We very rarely PVC, but it could theoretically be an azo dye. But it could be a cobalt. Now that cobalt is a CMR, it is officially one, but it doesn't actually become one legally, at least another year. I can't remember the exact date. Cobalt is not an uncommon source of blue or green in plastics. And people might be worried about, I now have, whether it's a medical device, now I got a blue medical device, it's got cobalt in it, I have a CMR. It's cobalt metal. The cobalt normally is a dye in PVC or otherwise, is something like blue 36, which is really a cobalt aluminum chromium oxide spinel. It's a different chemical. It's not cobalt. It's a cobalt aluminum chromium oxide. And so even though cobalt is creating the blue, it's actually a cobalt aluminum chromium oxide chemical. It's a very different chemical than cobalt itself, which is elemental. So the colorant is here, and that's where we normally think of what creates the color, but it's part of the carrier or PVC. Then there's a shade. So to whiten something, you add titanium dioxide, normally in plastic. Now, whitening it also makes it more matte. So taking a bright color, making it more matte, you add titanium dioxide. If you want to make it darker, you add carbon black, and often you add both, actually. You have one to make it matte and the other one to make it darker. That's the shade, titanium dioxide and carbon black, which are both Prop 65 substances. However, they are only Prop 65 substances when they're inhalable. So again, if you look at a safety data sheet and it says Prop 65, titanium dioxide and carbon black, that's because the safety data sheet is for the bag of pellets and flakes, not for your cable. It's for the inhalable. So that safety data sheet is not for your cable, it's for the bag of pellets where the dust can be inhaled, and they have to provide warnings for titanium dioxide and carbon black. When it's embedded in the final PVC version, it's not an inhalable risk. So titanium dioxide and carbon black are not a Prop 65 risk for that cable, even though they are in the plastic. They're embedded, they're not inhalable. And this is a very common disconnect you're going to see between suppliers and your product for Prop 65. If they base the data off the safety data sheet, that's the safety warnings for the safety data sheet. That is not necessarily, in many cases not at all, what the warnings would be for the plastic itself. And then there's often an optical brightener. So Most of the color you see is because the plastic or other material takes invisible light and either reflects it or absorbs it and re-emits in a different wavelength colors. And so everything basically in sunlight is all roughly similar levels of color. They're all different colors, but the brightness is really similar. Optical brighteners are chemicals that take in UV light, absorb it, and then re-emit in the visible. So they make use of a wider spectrum of the visible light. Well, they take in the UV and releases as visible light. So anything that uses optical brighteners, which are again more and more common, will have more pop because it'll be disproportionately bright compared to everything around it, because it's not just absorbing visible light and re-emitting, it's absorbing UV light, extra light, and re-emitting. And you see this very commonly in, say, a pool floaty or a pool ring. It's an inflatable PVC pool ring. You'll see those colors just pop right out of it. They normally have optical brighteners in it. That absorbs the UV and re-emits in the visible light, which allows even more light to come off that color than others around it. It's the optical brightener. Now, generally, the optical brighteners are not regulated right now. None of them are particularly dangerous or not seen to be dangerous yet, but it's another material that's generally in there. Big thing about colorant is you have a base PVC carrier. That PVC is PVC in of itself also. It has the base resin, but it also has often a plasticizer, usually lower concentration than the main PVC, but it has its own plasticizer. It also has its own antioxidant. So when we see BPA in PVC, if it's around 2,000 ppm, it's from the plasticizer. If it's around 500 ppm, it's from the colorant. If it's around 10 ppm, it's the antioxidant for the base PVC, or at least partially. And so this is not uncommon, where you have DHP getting into the PVC from the colorant. So when we measure for, say, orthophthalates like DHP or DINP or whichever in a PVC tube, when it's 100,000 ppm, it's because it's the main plasticizer. When it's 2,000 or 3,000 ppm, which is a non-compliance for RoHS or EU MDR, it's from the colorant. It comes in through the colorant. And so, and this is very common. We see this maybe 1 in 10 or 10% of all flexible PVC. We see these low levels, 2,000, of orthophthalates. Now, if you see 300 ppm of DHP, that's usually a contaminant from totem. Totem, the trimellitate, when it's esterized in a totem, also esterize residual phthalic anhydride, and you get a tiny bit of DHP, usually about 300 ppm. When you see a 2,000 or 3,000, it's coming in through the colorant. And this is a very serious mistake, a non-compliance mistake a lot of companies make, where they basically, hey, we're going to control the PVC, and then I want it this shade of blue. That shade of blue is a separate PVC. It has to be controlled as well, whether by yourselves or your suppliers or whichever. It is a compliance problem. And we see this in consumer products, but we see these in high-end medical, professional. It's super common, where the phthalate or the non-compliance is from the colorant. And this also is where we get DHP failures in rigid PVC. Rigid PVC doesn't need DHP. It doesn't have a plasticizer. However, the colorants for PVC, flexible PVC, can also normally be used for rigid PVC. And so rigid PVC ends up with these non-compliant levels of phthalates because of the colorant. It doesn't have to be. And they're usually quite capable of not having it. But it's very, very common. We see drawings all the time. It's basically, this is the PVC I want, and the grade, and even part number and supplier, and then we want it to be blue, or some RGB, red, green, blue, or some other, or Pantone. I want it to be this Pantone. Awesome. It's a separate plastic, by the way. So you either have to control it or the supplier has to control it. Somebody has to control it. Otherwise, getting this in is pretty common, where we get the phthalate. So pigments are probably the most misunderstood part of the plastics, where usually the pigment is a plastic in of itself with its own resin carrier, its own PVC carrier in this case, with its own plasticizer and antioxidant. So it's a big part of understanding the entire PVC. Where we see non-compliance for DHP, yes, we do see non-compliances for high concentrations all the time, but we also see it for a couple thousand ppm pretty darn often coming from the colorants. By the way, again, if you have any questions, there's a question thing down below, a little section. If you wish to add comments or questions. I'll try to get to as many as possible. Again, the idea of the webinar is about 50 minutes long and then get to Q&A. It went very slightly long this morning, but we got through the material, I think, fairly efficiently. Unfortunately, I speak a little bit quickly sometimes, which has its pros and cons. There's a lot of data. If I don't slur or I can still make sense, we'll see where this goes. This morning I had 2 cups of coffee. That probably made it for exciting reading. The recording's probably awesome. On the bright side, our new recordings, when they go up in a day or two, will also be on YouTube, but you can scroll it back to about 70% speed. My mom prefers 50%. Goodness love her, but make it a lot easier. So, getting back to the stabilizer. So the stabilizers, almost all PVC has stabilizer, and it usually needs a thermal stabilizer. Otherwise, the PVC's physical properties change dramatically with temperature, and usually it's the durometer, where the softness or flexibility changes heavily with temperature, and they need a stabilizer. And classically, the main stabilizers for PVC were dibasic lead stearate or dibasic lead sulfur acid, or barium cadmium stearate, stearate being soap, so barium cadmium soap, which are also, if you know your SBHCs, like I'm sure everybody does, those are actually SBHCs in of themselves. So from a RoHS point of view, it doesn't care. The lead is a failure and the cadmium is a failure. Historically, when we go and you go to your old Xerox machine, your photocopier, and definitely dating ourselves, and you test the outer jacket of its power cable, you get lead all the time. Leaded stabilizers, dibasic lead, is the main stabilizer, thermal stabilizer historically for PVC. And we still see it. So especially as we get to cheap plastics, like your dollar store type plastics, we get cadmium failures all the time. Cadmium in particular is a very good stabilizer for transparent PVC. We find it in other things, but in transparent PVC, it's an excellent stabilizer. And so for cheap plastic, we see cadmium in transparent PVC all the time. And it could just be the clamshell, actually. It's very, very common. Lead we see in PVC a lot. Your hookup wire has been slowly getting away from it. We used to see lead in hookup wire all the time. And that was the main RoHS non-compliance for hookup wire. It was the lead in the PVC, not solder. It's the lead in the PVC itself, and that's because it's a very effective thermal stabilizer. Now, for the most part nowadays, there's zinc or calcium stearate, zinc stearate or calcium stearate stabilizers, basically zinc soap. But they can also be organotins. And we do see organotins, which are regulated and reach SBHC or reach restrictions, depending on which one. Often enough, the most common at over 1,000 ppm is DOTE, DOTE, the octyl tins. We definitely see the octyl tins. Infrequently, we do see them over 1,000 ppm. We very rarely see the dibutyl or monobutyl tins over 1,000. We see them all the time at 20 ppm or small numbers. We don't see them in high concentrations. But organotins are also a very common stabilizer and regulated either as reach restrictions in consumer products or as SBHCs under reach. But also a lot of PVCs have UV stabilizers. If the PVC is outdoor rated, it has to be outdoors, PVC absorbs UV light and then has trouble re-emitting it. And that can then degrade or create sun fade or sun degradation of the PVC. So outdoor rated plastics often have UV stabilizers like UV320 or UV328. The reach SBHCs, the benzotriazoles. They're very common UV stabilizer. We don't see them that much. We're more likely to see those particular benzotriazoles, UV320 and such, in EPDM, outdoor rated EPDM or coax, but we can see it in PVC. It's rare, but if it is there, it's well over 1,000 ppm. So the stabilizer itself often contributes heavily to the potential of non-compliance with a cadmium or lead or organotins or infrequently the UV320s, etc. And then there's the antioxidant. Usually the PVC itself has an antioxidant. However, rarely is the BPA antioxidant PVC above 0.1%. It's normally from the plasticizer. It's the high concentration antioxidant in the plasticizer. The antioxidant, again, making it so when the PVC is extruded or otherwise processed, it doesn't react with oxygen and create a burnt effect, which is like color or oxidation, a color change, and possibly a materials change. It's often antioxidant, but almost always, if it's part of the base resin, it's well under 0.1%. When it's above 0.1% by weight, like bisphenol A can be in PVC, it's normally coming in through the plasticizer. And then there's the lubricant. Now, I'd often argue the lubricant's a different material. It's not the jacket itself, but this is usually inside the cable where there's silicone oil, or for large cables, talc is added. And that's to create lack of friction or fluidity between the outer jacket and the inner wires. You don't want them sticking because they can bind and cause problems, especially for flexible ones. So there's a lubricant added, which is often silicone oil, that allows it to slide. Now, one of the biggest non-compliances there is in the larger cables that use talc. So if you ever cut a larger power cable up and look inside, and there's this white powder, like baby powder in there. That's what baby powder used to be. Talc is asbestos with a much better marketing group. It's aluminum manganese oxides. They're both crystalline structure. They have very similar properties. It just has better marketing. One of the problems with industrial talc is it's normally co-mined with asbestos. And so very commonly, maybe 1 in 3, maybe a little less now, when we find talc in a power cable, we find asbestos, which is a Canadian or Australian non-compliance, where we have the asbestos contamination, the talc. And it's one of the many reasons why baby powders are now cornstarch instead of the original talc, because talc has most of the properties that asbestos has, and has some of the same negative effects, and often can have asbestos right in it. So those are the main materials in plastics. Now, what does it really mean for restricted materials? Well, this is substances we find all the time. Phthalates is the plasticizer as the main plasticizer. Short chain chlorinated paraffins is the secondary plasticizer with the orthophthalate. Antimony trioxide as the synergist to the halogenated flame retardant. We could find brominated flame retardant like Deca BDE, or chlorinated one like Chlorine Plus. The pigments can have their own plasticizer, and that's where we get a lot of low concentration, 2,000 or 3,000 ppm non-compliances for phthalates. It can have its own antioxidant, usually really low concentration though, not normally a failure. They can have azo dyes, infrequently in plastics, more likely in other things. Pigments have this tremendous ability to have non-compliant. And then titanium dioxide and carbon black, which, even though they're Prop 65 substances, only in airborne form. So once it's the finished cable, the titanium dioxide and the carbon black are no longer Prop 65 substances. And in effect, antimony trioxide is the same, actually. It's a Prop 65 substance, but it's really only inhalation. And so as long as your product's not inhalable, antimony trioxide is not a Prop 65 substance either. We get to the stabilizers, where we find lead and cadmium commonly enough, especially in cheaper materials. If you go to cheaper parts of materials, cadmium and lead are very common RoHS failures in PVC because they're the stabilizers. Organotin, infrequently, but we do get dioctyl tin, over 1,000 ppm. And if it's UV rated or outdoor rated, we get UV 320, 328 infrequently, but because it's UV stabilizer. So all of these, just one little plastic, has all these risks of having non-compliances. And we've had most of these. In the past year, we've had virtually every single one, at least for 1,000 ppm. And then the and the phthalate one, both in the bulk plasticizer and in the pigment, are very, very common. We get these every single week. Lead and cadmium PVC we get relatively commonly also. But the ones in the plasticizer or in the pigment are super common. Which always blows my mind is anybody doing EU MDR and not testing is taking an enormous risk, because we look at the complexity here. If you turn out not to have any restricted substances, awesome, your data matters. If you have a restricted substance in your product and you haven't tested, you're in a lot of trouble, because the national authorities don't care what your supplier told you, because they're used to dealing with cheaper products where the dollar type stores always say, hey, look, my supplier said it's fine. And they we don't care. Did you actually test for it? And so if you haven't tested for anything and you have a non-compliance, this is going to be a big, big, big problem for the medical devices. The whole thing can be taken right off the market, because you're looking at invasive or fluid contacting situations where you're causing harm or potentially causing harm. Very, very risky. But this goes for other products that don't have the same human health impact. These are very common non-compliances. The nice thing, if you have tested and done, and that's the main due diligence. Supplier documentation, by the way, is not due diligence for national authorities. They don't care. It can be used as a conformity assessment, and as long as you don't have a non-compliance, it's fine. Once you have a non-compliance, they only care if you've tested. And the reason being is the entities they normally have non-compliance events with always say their supplier said it was fine. It's like my dog ate my breakfast. They do not care. All they care is against the value of your sales. They expect you to be reasonable. You've done sufficient testing. If you haven't, they have no sympathy for you. Supplier documentation does not help if you have a non-compliance. If you've used it to help ensure you have non-compliance, sure, that's awesome. But once you do, it only matters whether you've tested. If you have tested and things go wrong, there's usually virtually no penalty. So back to the skip database, the big thing coming up. Database is supposed to be open in January, probably February is more likely, but not that late. And then you have to register any of your products that have an SBHC in any component above 0.1% by weight in it by Jan 5th, 2021. And for example, almost all electronics will have SBHCs. The lead and brass is super common. Not to mention button cell batteries, the D6 in siloxane, all the different chemicals in PVC. The chance of you having a declarable SBHC is very, very high in the average product. Just a reminder, it needs to be done. We have lots of good services in it. One of my most popular course right now, we're still learning, is the workshops, where we send somebody there normally. And we do some education, but more of it's hands-on. Like we take your product apart and point out the materials and say, this is the material that likely has this chemical. And then we create the declaration. And you can go further and verify whether that material does or does not have it. But at least we can create the declaration. And then once we create the paper version, we create the skip version. You get an idea of what the submission looks like and gives you a better idea of how to expand the information across a larger family of products. Well, most companies we work with have products that represent larger families, and how better to expand it across larger families of legacy products in particular. Testing, we do tons of testing. Virtually everybody sends their new designs to us because they have a compliance budget anyways. The compliance is so much easier for restricted materials. We just test it during the design and prototyping and pre-manufacturing, and create a gate to get into manufacturing. As long as you have this document, same as you do for electrical safety or EMC, you're fine. Legacy, it's more selective. We do more selective or representative product testing for due diligence and to further the compliance of larger product segments. And of course, we do skip declarations and submissions, where we usually start with Google Sheets. You'll find from a tangibility point of view, it's much easier to work with when multiple products and multiple internal stakeholders. It's a lot easier to work with. And once that's worked with and reviewed, because often you're going to want to review what you're submitting before you submit. And it's really easy to do in Google Sheets as opposed to sending around Excel files. Then you agree upon it, and then submission is relatively straightforward. And there will be, XML data type stuff. The chance of the XML data having error and causing lots of problems is so high whenever you submit. Usually, and there are exceptions, you got a million products same type, it's usually easier just to do it manually. Expect it to be easier. So we're going to do Q&A in a second. Don't forget about the skip database. I hope everybody learned something today. It's a kind of a technical field, and feel free to ask questions about it. We get lots of questions on plastics because we find non-compliances all the time in plastics. And PVC in particular is a very common source of non-compliance. And it's a good example because for one reason or another, it's generally half PVC resin and half other stuff. And the other stuff often has things that are now more regulated. So again, if you have any questions, feel free to submit it in the control panel, and I'll try to get to as many as possible.